Good afternoon. My name is Leah Shobe. Myself, my colleagues Joey Dickens, and Reza Tahiri, we're all here to talk to you about what's new in performance for vSphere 5. So before we get started, I'd like to see a show of hands of how many folks are deployed on 4.1 today. Very nice, very nice. Well, I'm hoping that by the end of this presentation that every one of you will make plans, if you haven't, to go ahead and migrate to 5.0. So let's talk about first what's new in Scalability and vSphere. So throughout the history of ESX, we have given you more and more resources to be able to build the largest VMs. Now, we have given you the resources to build the largest VMs in the world, with 32 vCPUs, up to 1 terabyte of memory. Now you can get 20% more throughput, and we've measured over 1 million IOPS for your performance. So, since we are going to make this 32-way VCU scalability available to you, we wanted to make sure that it could truly scale. So we went back in the lab and we did lots of measurements with Tier 1 applications, the type of applications you would put on this server, and we found that we were able to scale above 90% to native hardware. So we were very convinced that you're able to scale with your Tier 1 apps and mission-critical applications with the largest VMs in the world. We also did improvements with the CPU scheduler and also with vNUMA so that you can take more advantage and make things more efficient on the underlying NUMA hardware. With vCenter, VMs per cluster, we now are able to have more than double the throughput for management operations, and we have improved our latency by 75%. For HA, we now have faster failover. We measured 32 hosts with 3,200 VMs and wanted to configure an HA-enabled cluster, and we were able to do it 9 times faster than we were able to do it before. Minimal recovery time. From failure to first VM starts, we improved that by almost 50%. And 60% more VMs fail over in the same amount of time as it did before. So let's talk about what's new in networking. Network I/O control is a feature that came out in 4.1. For those of you not familiar with network I/O control, it is a traffic management feature on our distributed switch. In consolidated deployments, you're able to allocate chairs and limits for different traffic types, provide isolation, and also guarantee service levels for different types of traffic. So what we did for vSphere 5.0 is we added user-defined network resource pools. We also have a new traffic type for host-based replication, and we also included QoS tagging. So to show you an example of how you can improve your performance with network I/O control, on the top of the screen, it shows that we have a vMotion going on there. And as that vMotion is going on, it's grabbing up resources from the other traffic. And so then we see a performance impact in our latency and throughput for other types of traffic. But when we enable network I/O control, as you can see, we're able to control the resources that it's allowed to take, and it also finishes in relatively about the same amount of time, but the most important thing is that it has not impacted the traffic of other traffic types. They do not see a performance hit here. So it's a good way of being able to balance your load and be able to make sure that everybody can play nice in the sandbox. So for vSphere 5 with network I/O control, we're able to give you a higher granularity of control in being able to prioritize your workloads. So users can create new resource pools that are associated by port groups, and these tags can be added by priority for application or workload, which is a higher granularity than what we had before in 4.1 with predefined resource pools. So another feature that we have is split RX mode. Now, this greatly reduces packet loss. We were pretty impressed with this. And so this is a new way of doing network pack receiving processing for our VM kernel. So we did a little experiment. We ran more than 24 VMs, and we powered them on, and we observed that we got upwards of 40 plus in our packet loss. When we enabled split RX mode, it reduced it down to less than 1%. This will greatly help out your performance and keep your performance maintained. So to enable split RX mode, you can do this per VNIC, and you just edit the VMX file. Other features that we have here, our multicast performance improvements, you will see greater throughput, and you'll see a better efficiency with your CPUs. We also made improvements with the TCP/IP stack so that you can have higher throughput with small messages and better I/O scaling for your iSCSI traffic. So basically, what does all this mean for Tier 1 apps? This allows you to make sure that your mission-critical applications have the right amount of bandwidth and performance that it needs, and you can do an SLA guarantee. For multi-tenant environments, service providers who are deploying public clouds and are serving multi-tenants can now provision resources per tenant for their needs. NetFlow is another feature that we've added. It allows you to be able to collect all the IP traffic that's going across the bus and be able to send that to a third-party collector. That third-party collector then puts it into a report and allows you to see who's using the most traffic. Do you have any irregularities in behavior? And you can look at the number of bytes of a particular flow over the last 24 hours. So NetFlow we can use for performance management and monitoring. Capacity planning, it'll help you be able to make sure that you have enough resources for your most mission-critical applications, and also for your lower-level applications, you may want to be able to prioritize them a little bit lower, and so this gives you a chance to plan that. So visibility into virtual infrastructure traffic, whether it's intra, intro, or VM to physical, you'll be able to see it all. So let's look at what's new in vMotion. So this one was pretty excited, multi-NIC enablement. This allows you to use more than one NIC. And we did an out-of-the-box measurement between 4.1 and 5.0. And we found that just out of the box, we were able to get up to a 30% improvement in latency. So then we added the second NIC so we can enable multi-NIC enablement, and found that we got an additional 50% improvement in our latency. Storage vMotion, we now have live migration. For 3.5, we had snapshots, and people were pretty happy with that. And then we ended up going to dirty block tracking for 4.0, and people were very happy with that. We increased the performance of a vMotion a lot more with minimal downtime. But now with 5.0, we have I/O mirroring and live migration. And some of the advantages of doing this is now we have zero downtime. So customers that need to move their VMs, they don't have to power them on and power them off. During the time when you want to do upgrades on your storage, on your file systems, or even on your hardware, you don't have to power down your VMs. We offer both manual and automatic storage load balancing, so you can either do it manually with storage vMotion, or if you would like to be able to have it automatically done so that you're not constantly tracking it all day long, you can use storage DRS. And Joey will be talking about the details of storage DRS in a few minutes. And I would tell you to go to the DRS class, but since this is the last day, you won't be able to make it. But I'm sure Joey will be able to fill you in on the details of that. And then live storage migration increases VM mobility. So VMs are no longer pinned to the array that they were instantiated on. Live migration works by copying the memory and the device state of the VM from one host to the other. So this gives you negligible downtime. So now I'm going to turn the presentation over to Joey, and he's going to talk to you about what's new in memory management and in storage.
Excellent. Thank you, Leah. So my name is Joey Dickhands. I'm a performance specialist in technical marketing. And so I'm going to go over some of the new memory management features we have in vSphere 5, but I just wanted to recap that we've done a lot of new memory management features over the last few years. Last year, you might remember in vSphere 4.1, we introduced wide NUMA support. We also had memory compression being introduced in 4.1, and memory compression is an alternative to EXX level swapping. So let's look at some of the new features we have in vSphere 5 for memory. As Leah mentioned, we now have virtual NUMA support. Virtual NUMA allows us to present the physical NUMA topology of the physical server to the virtual machine and thus to the guest operating system so that any NUMA-aware applications running inside the guest operating system can take advantage of the NUMA topology of the physical server that it's running on. We also introduced host cache, which is another memory over commitment technique that we have. This allows us to utilize solid-state storage devices as a cache location for memory that's being swapped out. And we'll see these two features in a little bit more detail here. So first, our virtual NUMA technology. So virtual NUMA and NUMA is becoming more and more important to us as we see a lot larger physical servers in our data centers. And we're also seeing a lot larger memory-intensive workloads running in our virtualized environment. And a lot of these very large memory-intensive applications are becoming more and more NUMA aware as they need to take advantage of the memory more efficiently. And so NUMA, hopefully you're somewhat familiar with it, the non-uniform memory access. And just in case you're not familiar with it, we have a small little example here where we have two banks of memory inside the physical server. One bank of memory is being handled by processor 1. The other bank of memory is being handled by processor 2. Now, if you had an application that was running on processor 1, it'd be able to access the memory that's local to that processor, being handled by that processor, a lot faster than it would if it had to access the memory that's being handled by processor 2. All right, so that would cause this non-uniform memory access. Basically, the amount of time it takes to access memory depends on where you're running on the processor and what memory is associated, what memory you're using. So now when we first created virtual machines, we fully virtualized the memory. And so if we created 2 gigabytes of memory in our little example here, that memory would be presented to the virtual machine as one flat chunk of memory. Now, that was good. However, any application that needed to run in that environment didn't get any of the information on exactly where that memory was in the physical box. In most cases, it wasn't really necessary. However, as we get larger virtual machines and more demanding memory-intensive applications, they do need to know where it is. And so now with virtual NUMA, we're able to enable the virtual machine and give it information about where that memory is. And so we present to the virtual machine the 2 banks of memory as it is in the physical server. So now the guest operating system and any applications running in the guest operating system can more intelligently schedule their threads and schedule their memory usage in order to fit within inside the memory domains here and be able to take full advantage of the memory. Now, we have run a couple of studies with virtual NUMA, but I'll let Reza go on to those a little bit later in the talk. I will say that the performance gains using virtual NUMA, especially for very memory-intensive applications that are NUMA aware, are quite significant. All right, the other memory feature I wanted to talk about is host cache. So host cache is the idea of utilizing solid-state storage devices as a swapping cache location for these memory pages that are trying to be swapped out to disk. And the whole idea here is that an SSD device is significantly faster than your traditional rotating media. And so here, what happens is, if we have an SSD device and it's connected to our EXX server, vCenter will detect it, EXX will detect it as an SSD device, and it'll allow you to configure it as a host cache location. So you go into vCenter, you see your SSD device, and you can configure that SSD device. You don't have to configure the entire SSD drive. You can configure it in increments of 1 gigabyte. And you can assign that space to be used as host cache. And then, if you do have memory pressure in your environment, and you have to start doing some technologies to relieve that pressure, we go through the entire list first. We use transparent page sharing, we do ballooning, we do memory compression, that was new in 4.1. And then if we've exhausted all those other techniques and we do have to swap a page out to a swap location, we first attempt to use host cache. And so that memory page will go into the host cache location. And because it's on SSDs, it's a lot faster to write to it, it's a lot faster to read from it. Now, if we exhaust the amount of space we have available in host cache, the least recently used page will end up in its swap file, whichever page of memory that is, whichever VM is creating that page, it'll end up that VM swap file. So really, it is just a cache location utilizing SSDs. It's pretty impressive technologies, and we're able to get a nice little performance gain out of it. So we're able to get an additional 30% performance gain out of using host cache in conjunction with all the other memory overcommitment techniques we have. All right, so those were the two new memory management techniques we have in vSphere 5. Let's look at some of the new storage features. So new in vSphere 5 is the ability to use storage I/O control for NFS. We've got storage DRS. We are going to have a little update on VAAI. I'll mention all these in a few seconds here. And then I wanted to go over a couple of new performance studies we've done with the storage architecture in vSphere 5. All right, so let's see these in a little bit more detail. For those of you who were at VMworld last year, we did present this slide once before, but it is an important one. Storage is one of the biggest causes of performance problems in our virtualized environment. So we do need to address storage, and we have over the years provided more new techniques for trying to manage and control our storage in virtualized environments. And we've introduced disk shares quite a while back, and they worked well for quite a while. However, as our virtualized environments are getting larger and as we're running more diverse storage-intensive applications in our virtual environment, we noticed that there could be a potential imbalance of storage performance. So here in our little example where we don't have storage I/O control enabled, we have 3 virtual machines. We want to give them all about the same equal storage performance. So we have assigned them all equal disk shares. But what happens here is that virtual machine C, which has the same shares as A or B, actually is getting twice as much storage performance than either virtual machine A or virtual machine B. And that's because it's running all by itself on a separate EXX host, whereas virtual machine A and B are sharing one EXX host. So that's not exactly what we want to do. We also are not controlling the storage latency at the storage array in this environment. So we introduced storage I/O control. It was introduced in vSphere 4.1. And when we introduced it, we only introduced it support for Fibre Channel and iSCSI block devices. Now in vSphere 5, we've extended the support to include NFS data stores. And storage I/O control provides us that control in order to be able to balance out our virtualized environments and make sure that our virtual machines get equal and fair access to that storage. So now what we're using is storage I/O control to monitor their latency at the storage array. And when we detect that there is storage pressure, that there's contention at the storage array, we start throttling our workloads and balancing out the storage performance. So here you can see that VMC has now been throttled back a little bit so that it's not able to hog all the storage performance, but it gets equal amount of storage performance compared to VMA and VMB. So now that we have storage I/O control support for NFS in vSphere 5, high priority critical virtual machines running on NFS data stores using storage I/O control can all get all the benefits that we were able to provide virtual machines running on Fibre Channel and iSCSI before, which is increased storage performance, limits performance fluctuations during I/O congestion, increased throughput, decreased storage latencies. So 2 other features we introduced in vSphere 5. The first is just the ability to pool individual data stores into a resource pool, a storage pool. And we call this pool a Datastore Cluster. Now, in a very simple Datastore cluster, really all it is a pool of data stores where you can then deploy virtual machines or VMDKs onto those data stores, but instead of assigning it to a data store, you assign it to a pool of storage. And you can then choose which data store individually is inside that pool. Now, if you want it to be a little bit more advanced, you can use storage DRS. And when you enable storage DRS on a Datastore cluster, it'll do load balancing and make recommendations on where to place that virtual machine in your environment. And so when you use storage DRS with a Datastore cluster, the Datastore cluster basically becomes a load balancing domain, very similar to what we used for a DRS cluster at the EXX host level. So let's look what Storage DRS provides in a little bit more detail here. So the first thing that it provides is initial placement. So just when you first power on that virtual machine, it asks you where do you want to place it when you create it. And it makes a recommendation based on the capacity that it's detecting in the individual data stores and the amount of I/O load being generated on each of those individual data stores. So it'll make a recommendation for initial placement. The next thing it is able to do, it's able to make ongoing monitoring and recommendations of your data stores based on capacity. So it'll keep an eye on all of your data stores in the Datastore Cluster, and if it notices that one is beginning to run out of space, it'll start making recommendations, or you could have configured it for completely automatic mode, in which case it'll actually do a storage vMotion for you and migrate some of those virtual machine VMDKs off of that data store onto a less congested, higher capacity data store. The other thing it's able to do, very similar to ongoing capacity monitoring, it's able to do ongoing load monitoring on the data stores. So it's able to detect if one of your data stores is getting saturated. It's able to then do a storage vMotion to one of the other data stores that has less I/O load on it at the time. And a couple of rules that it's able to do. We've got VMDK affinity and VMDK anti-affinity. So if you want to have all the virtual disks for your VM move with it, so if it does need to make a recommendation based on capacity or based on I/O load, it'll move all the VMDKs associated with it. That is the default, the affinity rule. You could also have the opposite, so you can have anti-affinity rules where the VMDKs are spread across all the data stores in the Datastore Cluster. All right, so I wanted to touch on this one as well. So VAI are vStorage APIs for array integration. This was introduced in vSphere 4.1 as well, but when it was introduced, it only had the first three primitives, the full copy, block zeroing, and hardware-assisted locking. Now in vSphere 5, we have introduced thin provisioning monitoring and dead space reclamation. Now it's really the first three that we introduced in vSphere 4, the full copy, block zeroing, and hardware-assisted locking, that provides you the big performance gains. But I wanted to mention this VAI technology again, just to make sure that you are aware of it, and because it provides a great benefit to those customers that are making their journey to a very large cloud infrastructure environment. Cloud infrastructure features like VAI will become more important to you over time. And it's not just because VAI provides you a time saver. So if you think about VAI, what it's able to do, it's able to offload the common storage tasks that vSphere has to do to the storage array itself. And the storage array is able to process it and then respond back to the vSphere or the EXX client saying it's done with the processing. So we're able to offload to the storage array when we use VAI. And by doing so, we can greatly speed up our cloning times. So here in this example, we were able to get a 95% reduction in the amount of time it took to clone a virtual machine when we were able to use the VAI technologies. But it's not just a benefit in time. We also get a benefit in CPU usage and memory usage on our EXX hosts because we're able to offload a lot of the heavy lifting to the storage array and make the storage array do that processing instead of having the EXX server do it. We also see gains and performance gains by not having to utilize the bandwidth of our network if we're using an iSCSI or an NFS data store, or our pipe if it's a fiber channel connection. So we see greatly reduced bandwidth utilization on the pipe if we're able to offload the command to the VAI or to the storage array. We also see a reduction in storage load on the storage array, and this is because the storage array is greatly more efficient at being able to process the VAI offloaded command than it is to have to process the equivalent vSphere or EXX commands to accomplish the same task. So there's a lot of great benefits from using VAI. And if that didn't convince you to use it, here's yet another one. So we introduced the VAI thin provisioning support in vSphere 5. And thin provisioning is obviously becoming more and more popular. We have it at the virtual layer with your VMDKs that could be thin provisioned. And thin provisioning can occur at the LUN level, at the actual storage array level. Now, there is some concerns in the past about providing thin provisioned LUNs at the storage array level. And that's because there's no way to reclaim space. Once we've got a thin provisioned LUN and we've created a virtual machine in it and it's expanded, we have no way, if we've deleted the virtual machine or for some reason we've storage vMotioned the virtual machine off of that LUN, to tell the LUN that it can reuse that space. There's no way to shrink the LUN after, at least previously, there was no way to do it. Also, the other concern we had previously was that there was no way to really tell what the storage array, how much free space the storage array had. So from vCenter and from EXX's point of view, it might look like the LUN had lots of free space on it. The VMFS file system didn't look like it was being very heavily utilized. But on the back-end storage array, we might have been running out of space. And if the back-end storage array completely ran out of space and the LUN couldn't be grown at the storage array level, all heck could have broken loose. All of our virtual machines might not be able to write to the LUN because there might not be any space available to it at the storage array level. So using VAI, we're able to fix that. We introduced dead space reclamation. And here what we were able to do is we can detect that the space has been moved, and we can then tell the storage array that some of those blocks are now wasted space, and they can reclaim it. So here we have a simple example where we've got a virtual machine running on Datastore A, and we do a simple vMotion and move it over to Datastore B. That leaves some wasted blocks on Datastore A, and given the size of a virtual machine, it could be a lot of wasted space. And now using VAI thin provisioning, we're able to tell the storage array that those blocks are no longer necessary and that it can sort of dissolve them away into the ether. And now the thin provisioned array can now be told that those blocks are no longer necessary. Go ahead and rethin the volume. So all that space that it was able to reclaim can be used someplace else on a different LUN on that storage array. We also now have monitoring capabilities. We can detect that the storage array is running out of space and detect that and monitor and alert that to a VI admin through vSphere. So VAI technologies are pretty cool. Here's another cool little feature we were able to do, a little study that we did with some of our storage partners. We just recently completed a 1 million IOPS study. So for all those naysayers out there who have been telling us that, oh no, we're too scared of virtualizing our data centers because we run very storage-intensive applications, it's not true. You can virtualize those. Here, look at these numbers. We've got 1 million IOPS at 8K I/O size. So 8K is a more reasonable sized I/O for a production environment. Most vendors will publish the much smaller size, which is a little bit unrealistic, but we'll publish it as well. 1.2 million if we measure the smaller 512 byte size. So that's a phenomenal amount of I/O and number of IOPS being generated. And this is being done from a single EXX server, a single EXX vSphere 5 server. Now, in order to accomplish this, we did need some walk-in big servers. So we had our partner from Intel provide us with a 4-socket Intel server using 40 cores. We had some of our friends from Emulex provide us 6 dual-port Emulex HBAs to drive the fiber channel traffic. And then EMC provided a large VMax storage array in order to handle all the workload. And there's our 1 million IOPS number for Myometer. Now, another new feature we have in vSphere 5 is the ability to create software-based FCOE. And so we wanted to see how software-based FCOE would stack up. And so we compared it to native FC. So using software-based FCOE over a 10 gigabit Ethernet adapter, and we compared that to native 8 gigabit fiber channel. And we basically saw that FCOE performs on par at pretty much every I/O size as the native 8 gigabit. So that's pretty great, but what do we could do something big, heroic number here. We'd already done 1 million IOPS, so let's try to go for throughput this time. So we scaled out our FCOE environment, and we used 4 vSphere 5 hosts. And we had, in each of those vSphere 5 hosts, we had 2 dual-port Intel server adapters, and we drove about 16 streams of FCOE I/O traffic towards an EMC VNX storage array. And there you see we were able to get 10 gigabytes worth of total throughput going through the environment, all with just 4 vSphere 5 hosts. So very impressive. So now I'm going to pass it over to Reza, who will show you how these new vSphere 5 performance features are translating into better performance for our Tier 1 applications and giving our customers the confidence to virtualize their Tier 1 applications on a vSphere 5 environment.
Thank you, Joey. As Joey said, I'm going to show you some numbers and charts and graphs that show our performance with 5.0. I know you guys are tired after 3 days of conference and VMworld party last night and everything, so we'll try to keep it a little lively. And by way of introduction, I've been with VMware a little over 4 years, and before that I was with Bell Labs and HP for 20 years, doing pretty much what I'm doing now, working on high-end servers, optimizing their performance, in particular for database applications. All right, so this is a chart from last year. You guys probably have seen it. It shows what percentage of applications were virtualized last January. And then you go a year later, And you can see everything is at least a quarter virtualized, even some of the hard-to-crack ones like SAP and Oracle, and some like SharePoint are over 2/3 virtualized. And in my talk, what I'm going to give you is I'm going to give you a mix of some Tier 1 applications at a very high level, show you what performance looks like there, and also then go and, as by way of example, give a few nuggets of, in one particular area, in one particular feature, how it improves performance. I'm going to give you a mix of that. So we're going to start with high-performance computing applications. These are applications that require a lot of CPU. They are CPU-hungry, and they also use the memory bandwidth, caches, memory links very heavily. So what you would like to have for good performance is being able to use all the CPUs on the system. And you can guess I'm going to tell you that with 32 CPUs in a virtual machine, we have improved the scaling there. And also the NUMA properties, so non-uniform memory access properties of the hardware, are very heavily used by the applications, by high-performance computing applications themselves. They are aware of the NUMA properties, and they use it for best performance. What we use here is we did some internal testing, so we haven't published these, but these are industry standard benchmarks. These are benchmarks that everybody uses to measure high-performance computing applications. One was Spec MPI. That's an MPI parallel benchmark, heavy floating point, heavy processor utilization, and also Spec OMP, an OpenMP application that, again, is very heavy on processor and memory utilization. So first, let's talk about vNUMA. As Joey said, in vSphere 5, we passed the NUMA properties up to the guest. And let me show you why that matters. Without vNUMA, so before 5.0, the guest operating system, this blue chunk here, is not aware that the hardware underneath is NUMA hardware. So what we told the guest was that there is a single locality in the hardware. And so the guest application would say, OK, I'd like to put my processors in this locality. There is only one. OK, just put it there. And I'd like to put a memory near it. There is only one. Then put the memory there, too. However, underneath, we would stripe the memory for best throughput. We would stripe it over all the NUMA nodes. And as a result, you only had 25% locality, even though the guest thought it was doing the best. Now, with vNUMA properties passed up to the guest, you can see that the guest is aware, there are 4 localities. And then if it puts its processes on processors on locality 1, it says put the memory in locality 1, 2, and we will do it, and now you have full locality. And I'll show you in some charts later how much that helped us. So first, some results from Spec MPI. So the y-axis is native to virtual completion time ratio, how long it took to run the benchmark. So below 1 means native was better, and we have one data point over 1 that says for that one, virtual was better. But the point is that in these, if you count them, there are 16 bars here. There are 3 of them that are below 96%, and the other 13 are 96% and above. That says that the native and virtual performance are virtually, if I may use that word, identical. Give you an idea of how much we gained with vNUMA. The y-axis here is speed up. And what this says, for example, is that for LU with 32 processes, it's without vNUMA, if something took about 130 seconds to run, with vNUMA, it takes only about 100. Spec OMP may even be more impressive. If you look at the virtual to physical ratio, it's right around 90-95%, close to 100 in many of them, for 4 to 32 processes. But what's more interesting is you look at the speed up due to vNUMA. For this example, there is like a 2.6x speed up, which means that something that used to take 260 seconds now would only take 100 seconds to run. So to sum this up, using the 32 vCPUs and NUMA Properties, we can scale up to 32-way, very close to native. And the speed up of VNUMA for the mean of it for the two benchmarks is 13 to 25%. Okay, another tier 1 application, obviously, Microsoft Exchange. We use the standard Microsoft load gen benchmark for this with the very heavy user workload. We pretty much follow the Microsoft guidelines here. So they tell you not to go over 12 cores for a single Exchange instance. And they usually run 1,000 users per CPU. I think these days you can do more, but everybody is still sticking to 1,000. And you can see how underutilized the system is, even with 1,000 users, and even with all 12 processors that we can allocate. And we looked at both scale-up and vMotion. And if you guys came to my talk on Tuesday afternoon, we also showed some scale-out results with Exchange. Okay, so as Leah mentioned, the performance of a lot of these applications have been studied and optimized for release after release. So performance was already pretty good with 4.1, but it's still a little bit better with 5.0. If you look at the 95th percentile response time, it dropped from like, I don't know, it's like about 260 to about 230, from 4.1 green to 5.0 blue. And now we can run with 12, the maximum number of cores that Exchange is recommended to have. We can run with 12,000 users, and still the response time is below the 500 milliseconds. And the CPU utilization also improved. Okay, a few percent of reduction in the CPU utilization and a little bit of reduction in the response time. So we're still optimizing, we're still tuning, and we are going up to 12 CPUs. And on vMotion side, so let me tell you what we did here. This is a 28 gig guest. It's running Exchange with 4,000 users, right? And we are vMotioning this on a 10 gig link to a different machine. In 4.1, it took 71 seconds. And this is the number of tasks that got queued up. So what happens is that in that very brief moment that there is a hiccup while the last activity of the vMotion takes place, some of your users that were submitting transactions notice a little pause, they get queued up. But the number of exceptions is 0. Once you move over, the queue is emptied out and they move on. The improvement from 4.1 to 5 in terms of the migration time itself looks like it's around 1/3 faster, and about 1/3 fewer users got queued up. On the storage vMotion side, we moved a 350 gig VMDK file. So that's 2,000 users. Half the users were on this one VMDK that we storage vMotion to a different array. And the time it took is about 700 seconds. It's something like 100 seconds faster than 4.1. And very low queuing, and of course, no exceptions. You can pretty much do this without anybody noticing. If you want to tease your users, you can keep moving the file back and forth and see if anybody notices, just for fun. Probably won't even tell. Now, here is an example of one specific area. Not everybody will benefit from this, but the people who do are going to really appreciate it. This is Multicast split or exploit. So what this is if you have a bunch of VMs on a host, and you have a lot of multicast packets coming. So if it's, for example, a stock trade ticker, and is sending trade information constantly, thousands of them per second. If you have any day traders among you guys, that's just probably one thing you would notice. Or a typical bus. Again, lots of multicast packets. What we do is that they don't get sent to every VM because that's going to overwhelm the switch, everything. a single packet is sent to the vSwitch, and then it is replicated out to all the VMs on the host, right? That's a great benefit. However, you end up with one thread doing this replication, and you can bottleneck on that. And because of that, if the number of VMs is high, and if the packet rate is high, you could have some packet loss. And let me show you this. Okay, so the red dashed line is without the split RX mode. So this is what we had before. And 40,000 packets per second. 40,000 multicast packets per second coming into the host. And you can see as we replicate it to 5, 10 VMs, so y-axis is the percentage of packet loss. The x-axis is the number of receiver VMs. Up to 20, no problem. When you go to 24, 28, you can see there is a lot of packet loss. So it is a crazy rate, but still, we're trying to highlight, even at this crazy rate, what we can do. So at 40K packets per second, there is a packet loss up to 40%, 45%. With 30K, it's a little bit better. With 20K, no problems. At 20K packets per second, there was no problem. But even at 30 and 40, if you do enable the split RX mode, you can see 30K packets per second, the green line, no packet loss. And even 40K, you can go up to 28 VMs, still no packet loss. And at this point, now you still start getting a little bit congested. But for an application that uses this is a great boon. And I have two more performance improvements to talk about. One is, this again is for one specific area. So this is for people who use VDI. This is the View Planner benchmark. It's a benchmark we have published in white papers and blogs. You can go look it up online. And it emulates Office activity. So it has a number of transactions. It goes and opens up Adobe Acrobat, opens a PDF file, closes it, Excel, Word, open, close, doing your typical Office things. And on this 8-core 96 gig host, we picked it specifically to fit this. The CPU and memory are both pretty much fully utilized. With these 1 gig client VMs, and the passing mark of this benchmark being 95th percentile of responses have to be below 1.5 seconds. Up to 88 VMs, no problem. The response time is 0.96. You go a little higher, you see this huge jump. You run out of memory. It starts swapping. The machine, the 96 gig, is fully used, and you can see, 1 gig, 96. You start having issues. With 5.0, we improved the memory utilization, let's call it memory overhead, for lack of a better word, of each VM to the point that you can go up to 116 VMs. So that's about a third higher, 30% higher, and still have reasonable response time. And then you add more and you can see it dives, out of memory. Again, this is due to improvements in the memory usage of the system. So we, again, fully utilize the memory, but with 30% more VMs. And I think I saved this one the best for last. This is with SAP. And if you notice at the beginning, SAP was the application that had been the least virtualized. And what I like about this particular result is, one, obviously SAP is a real-world app. And second, so I know you all know SAP, but based on the last couple of talks that we gave, I'm guessing that not many people know of the SAP sales and distribution benchmark. Has anybody heard of SAP ST benchmark? Wow, nobody. Okay, so you guys should go look it up. This is an industry standard benchmark that is published and maintained by SAP itself. So vendors who want to publish, they have to get the results certified by SAP. So in fact, I was obligated to list the certification numbers of these results that I'm talking about. And the results were published by Fujitsu. We did help them, but it was a third party that published these. on a obviously modern high-end system, and they did something very interesting. They published 2 results, virtual and physical, on the same machine with the same everything. And the results are, if you look, these are the metrics that get published for SAP SD benchmark. Users and SAPs are the throughput metrics. And you can see that virtual is 94% of physical. So the gap is only 6%. And the response time is 1% slower, so it went from 0.98 to 0.99. And one other thing I really like about SAP SD is that the test sponsor is obligated to report the CPU utilization. So you can't, let's say, run physical and push it only to 60% and then push the virtual to 100 and say, oh, look, they are the same. You can see both systems are saturated, and the utilization of virtual is only 1% higher. Okay? And to highlight again the difference between 4.1 and 5.0, the highest number published on 4.1 was 2,000 users, and this with 24 vCPUs. Right, so again, we can go up to 32. We were able to do this with 24 vCPUs with 5.0, is like 2.2 times higher. So it's a great boost. All right, a quick nod to my colleagues who provided all the data on what I reported. And with that, I'd like to thank you for coming. And again, I know this is your 3rd day, probably tired, but hopefully the numbers didn't bore you. And please do fill out the survey on your mobile device. And if you have any questions, probably best if you come by later. Joey, Leon, I will be glad to talk to you. Thanks for coming.